So today's target was benzene. Till yesterday, we did everything about alkane, alkene, alkyne, and conjugate addition we did. Today we'll do benzene. Now, benzene is called king of aromaticity. Of course, the word aromaticity we have done in, I think, uh, second week when GOC was there. There was this information of what is aromatic. है ना? Still, let us revise cyclic planar conjugation and Huckel's rule of aromaticity should be 4n plus 2 is equals to number of pi electrons. And on solving this, n value should be any positive integer, right? 0 to any value, that is aromaticity. When we talk of benzene, its degree of unsaturation is 4, correct? Its degree of unsaturation will include the 3 bonds and 1 cycle. So degree of unsaturation is 4. But yesterday only we discussed, but still it will not be called an unsaturated compound because an unsaturated compound is a chemical condition which will give positive test for uh, bromine water and will give positive test with Bayer's reagent decolorization. If these two tests are not there, then it is not an unsaturated compound. It do not give bromine addition reaction or decolorization of Bayer's reagent like alkenes, right? Let's revise the methods of preparation of benzene. How we can prepare benzene? First and foremost, of course, is starting with soda lime. Okay, you can have either the benzoic acid or you can have the sodium benzoate. You can have more number of COH also, like phthalic acid or is तरह से isophthalic acid. Any one could be taken, and when this is treated with soda lime, right? This thing is soda lime, NaOH plus CaO. We did this day before yesterday in alkanes. This is soda lime. Then we get benzene. That was first method. Next is preparation from diazonium chloride. Now in diazonium chloride, when we prepare, this N2 is a very easily losable group, right? Even if we heat it beyond 5 degrees, then nitrogen is lost. So that reaction is used. If you heat it, nitrogen is lost and benzene is formed. But a similar and a very important reaction, diazonium chloride with ETOH will form benzene, and ETOH is oxidized to acetaldehyde. This is given in NCERT, so we have to be very clear about this, that with acetaldehyde also what we'll get is benzene. But if the reaction is with methanol, okay, then see there is no oxidation, it is methoxybenzene which is formed. This we need to remember, that with acetaldehyde we are having benzene, with methanol we are having methoxybenzene. Fourth method is with Grignard. We can have formation of Grignard, and then Grignard on addition of water will form benzene. That is a common source, common methods. All are known to you, I assume. Very, very important for us that phenol to benzene direct conversion single step is by zinc dust, and in this process zinc becomes ZNO. These days those integer questions come now, how much amount of zinc is consumed and all those. So this is how the change is, zinc is converted to ZNO. Now you can balance and do those integers if required. Okay, all these marked are important question. Then comes that this cycloaddition, red hot iron tube. If I have acetylene, right, then I will have this type of cycloaddition and we will have formation of benzene. Correct? This is yesterday's work. This is again old work, day before yesterday. Hydroforming or aromatization. N-hexane, then we got benzene. You can have N-heptane, then toluene. If you have octane, N-octane, then I can have either ethyl benzene or I can have, I think, orthoxylene, right? You just have to 3, 4, 5, 6, 7, 8. You just have to make these connections and you will have orthoxylene like this. Okay. But remember the catalyst is MO2O3, Cr2O3, V2O5. These are supported by alumina. Temperatures are quite high, pressure is high, and aromatization is taking place. There are other methods also of aromatization once the ring gets the cycle. Okay, here ring is not cyclic. The structure is not cyclic. They started with open chain and so these are the catalysts. But if they start with any cycle, at least loop is done. Benzene, cyclohexene, diene, any of this format, then please mark this as an important reaction, important reagent list, sulfur or selenium or palladium carbon. You heat with any of these. And there is also one more method which I'd like to add here is either this or you can take exchange of hydrogen. For example, I may have CH triple bond CH. So if this is there, this will be converted to CH3 CH3. It will accept the hydrogen which are removed from here. Okay, there is hydrogen exchange and the driving force is the aromaticity. If one is not getting aromatic, then this reaction is not of any such use. Is that absolutely clear how it is done? Benzene, cyclohexene, cyclohexadiene, any of these, then there is a hydrogen exchange or there is a gap. This is not SOR. Sulfur or selenium or palladium carbon heat. Any of these could be used. Then there is benzene sulfonic acid. If I take benzene sulfonic acid and heat it with any protic source, it could be HCl, it could be H2SO4, any at 160 degrees centigrade, then SO3 is removed. This is ipso reaction. Okay, we'll see later stages mein what is ipso. H plus is coming and SO3H is displaced. That is why it is called ipso reaction. Okay. Now we are going to chemical reactions of benzene. Now, chemical reactions, the benzene itself has a very high resonance energy, king of aromaticity, we are saying. So it is highly stabilized, 36 kilocalorie per mole. Now, benzene give electrophilic substitution reactions, not addition. If I will add, I will lose this aromatic cloud. So definitely that is not a possibility, not a choice. That is loss of aromaticity is not a choice. We have substitution. We represent either by SEAR. E here is electrophilic, S is substitution, AR is aromatic. Right? Electrophilic aromatic substitution or simply SE reactions. So E plus will come and H plus is displaced. That is what we are doing. Mechanism. Now we are starting directly by formation of a sigma complex. Though before this sixth step, there is one very obvious thing happens that this pi electron cloud, which is a benzene is planar, the pi electron cloud is upside and downside, both side. So when any electron deficient system approaches this entire electron cloud gets attracted towards E plus. So whatever was initially uniformly distributed is no more uniformly distributed. It will get pulled towards the E plus. And this we will call pi complex. Okay, this will called pi complex. This pi complex is like no sigma bond, no pi bond is actually formed. It is just by the attractive force of these electron and E plus. If at this point you remove E plus, if you just cut it out, then again you will get this status. Okay, and this leads ultimately to the bond formation. If this happens, then bond is now formed. So when I break a sigma and I form a bond which is resonating. See, this is a sigma complex which is resonating, and here is the hybrid sigma complex or Whelan intermediate or arenium ion, any of the names we can call it. Okay, so in that first step, we have lost the aromaticity. Benzene is no more aromatic, it is a resonating cation. But in step 2, we have to gain our aromaticity back. We want our aromaticity back. Now, when we want our aromaticity back, we have two choices. What are our two choices? Either I can lose H plus or I can lose E plus. So yes, if E plus is a reasonably stable leaving group, we can have loss of E plus also. Okay, but currently I'm showing loss of H plus and you have a substituted benzene formed. In step 1, if step 1 is the RDS, then no kinetic isotope effect will be observed, right? In E2 also yesterday I explained that if you use the heavier isotope, rate of reaction goes down. That is called the kinetic isotope effect. So, but if step 1 is RDS, then kinetic isotope effect is not found. If step 2, where there is a direct involvement of carbon hydrogen bond, if I change it to deuterium, definitely rate will be impacted. And so if step 2 is RDS, then reaction will exhibit Ki effect. Is that absolutely okay? That only if second step is RDS, then it will show the kinetic isotope effect. Sulfonation and iodination exhibit Ki effect. Still, I am not commenting that sulfonation and iodination have second step RDS. There is very, what should I say, very thin boundary line variations in the statements. I'm not saying that for sulfonation, iodination, second step is RDS. I'm saying just that they exhibit kinetic isotope effect. Okay. EAS of mono-substituted benzene ring. If I have a mono-substituted benzene ring like PHG, then what will be the effect of this G on E plus attack? Okay. So G will have two impact. First, either it is called activating, deactivating nature, or we have to take that in its presence, this E will now go to what place? I mean, with respect to G, new E will come at orthopara or meta position. So two things we have to study. First, activating, deactivating nature, and second is the directive influence of G, how it will direct the incoming electrophile. Now you have to be very clear that when I talk of activating, deactivating nature of G, it is entirely different thing. And when I talk of directive influence, it is different set. They may have overlapping properties, overlapping observations, overlapping groups, but they are not identical points. Let me clarify more. How to know that the group is activating, deactivating? Yes, theoretically, when we teach, we make you learn that these groups are activating, these are deactivating, and how generalizations can be done. But practically, it is only an experiment which tells us that this group is activating or deactivating. For example, or rather for theory, let me add, then I will take the example how it is considered. We take benzene. Benzene is attacked by E plus and we form this substituted benzene. Rate constant is K1. Okay. Now, when we take substituted benzene attacked by E plus, rate constant is K2. Now, we are not bothered that this E is going at ortho, meta, para, where it is going, that is not we are considering. We are just considering the kinetics of this substituted benzene and we say it is K2. So we'll have some numerical values. We have some data when we are in lab. When we get this data, then if K1 is greater than K2, it means in presence of this G, the same reaction rate has gone down, right? In the same reaction is getting less kinetically. It means this G is acting deactivating. Is that clear? That if it is so, then this G is acting deactivating. Is that absolutely clear? Whereas if K1 is less than K2, if K1 is less than K2, then what is observed? That as compared to normal benzene, this G is now having, what is it having? Faster rate. So what has this G done? This G has done activating and increase the rate of the same electrophilic attack. Then we'll call it activating. Now these terms are fine. There can be some generalizations that I'll share, but certainly only the experiment will be the final call taking thing, that we have to call this group as activating or deactivating. What we can do, I will add. Now it is observed that electron releasing groups are activating in nature, like OH, OR, O minus, NH2, OCOR, CH3, etc. All these are activating, and electron withdrawing groups are found to be deactivating, like nitro, cyano, aldehyde, ester. Okay, these both are, I have written aldehyde, so I'll change one as ketone. Okay, Cl, halogens is what meant, COR. So Cl, Br, I, F, COH, SO3H, again, etc. There will be some more. There is a possibility. And these are special cases which are minus I greater than plus R. Otherwise, most of the time it is the resonance which dominates. Okay. Coming to factor 2. What was our factor 2? That is the directive influence. That how the incoming group will be directed by the existing group on the benzene. Now see, E plus can attack either on ortho or on para, okay, or on meta. So all three I'm drawing. Don't worry. We'll draw all three. So if it is attacking at ortho, then these are my sigma complexes. If it attacks on ortho, then this G plus, then resonance and resonance. So ultimately I can say that there is a hybrid where H, E, G, here there is a del plus, here there is a del plus, and here where G is attached, at this point there is a del plus, right? Similarly, if I attack at para position, see, I attack, plus comes here, again resonance and resonance. So if I draw resonance hybrid of para sigma complex, the structure will be G, H, E, del plus, and del plus, like this. Correct? So this is how its hybrid will be. Plus adjacent to G here. Plus adjacent to G here. Okay. If G is meta, if E plus is attacking meta, then this is how I will get the positive charge. Again, I'll draw the resonance and let me draw the hybrid. This time E is coming meta to the existing G. So where will be my plus? My plus will be del plus, and del plus. This time G, say adjacent carbon pe there is no direct plus, right? Now see, if this G is electron releasing, let us take some example, right, for this statement. if G is electron releasing, so example OH. So if I have a G which is OH, then the plus adjacent to this, whether it is through ortho attack or through para attack. But if this plus has reached here, oxygen can immediately give the electron pair and form a bond. And there will be one of the resonating structure in which the octet is complete. So ortho and para attack is giving me this choice. Okay. If this G was electron withdrawing, let me draw. If it is nitro and this plus comes here. If I take nitro and plus comes here. Now this nitro itself is electron withdrawing. Here nitrogen is having plus. This plus and plus will be repulsive. So this is unstable. It is not good to have plus adjacent to this. And these are stable. So if I have electron releasing groups like OH, OR, NH2, OMe, and then what we'll found is that ortho para sigma complex is more stable than meta, and G is called OP directing group because the activation energy is the only criteria which will decide that ortho, meta or para where the attack will be. Okay. They will attack all possible. Whose sigma complex is most stable? That will be the one which will be preferred. And the one which is stable will take the lower activation barrier thing, and then that will be the conclusion. So for example, if I have nitro, it is wiser to move away from NO2, right? It is wiser to move away from NO2. Otherwise, what will happen is it will, I lost the page, it seems. No, it's all good. Why I can't see? Oh, yeah. All of you can see, na? Something happened. Coming back. So if G is plus R group, then ortho, para, and sigma complex is more stable than meta. If G is minus R like nitro, then meta sigma complex, and then the group is called meta directing. Okay. Now you have to predict whether it is ortho para directing. Please write in your rough notebooks or whatever you have in your hand, and I'll tell the answers. Okay, I'll try to tell wherever there is, as far my information wise, whatever activating, deactivating thing I can add, I'll add. But practically, it is not right that I can suggest a generalized thing always. Okay, so OH will be orthopara activating. For deactivating, I'll put D. NH2 will be orthopara activating because these have lone pairs, and these lone pairs will form complete octet structures. Now, how we are doing? We are imagining as if this is connected to benzene, and there what effect is being done by these groups. Okay, so if NHCOCH3, then I'll say it is orthopara and activating. OMe, orthopara and activating. Correct? CH double bond CH2. Now that is a group which can have both effect. It can have a plus R, it can have a minus R. But when I'm talking of rhenium ion, then certainly it will be better for a plus R effect. Cinnamaldehyde, when benzene ring will be there, it is orthopara. Yes, this will be in cross conjugation to this side and to the benzene ring. It is found to be weak deactivating. But yes, it is deactivating. Okay, overall impact. Electrons go more this side. Coming to cinnamic, same thing. Orthopara deactivating. Clear? Nitroso. See, there is a lone pair on this. It can donate, but overall impact is withdrawing nature dominates. So it is also found to be orthopara and deactivating. Nitro is meta and deactivating. I hope you are able to make some notes if required, though I will share mine. This is meta deactivating. Halogens are very, very important. Yesterday, we discussed vinyl halide पे addition of HX when we were discussing alkynes पे HBr का addition. Similar concept we have to use again. Okay, so fluorine, chlorine, bromine, iodine. Now, what will be the observation? They are orthopara directing but are weakly deactivating only. They will deactivate. How and why? So, the reason you will say is that when chlorine is here and I form a orthopara sigma complex, in absence of chlorine, there is no electron withdrawing. But if chlorine is there, minus I is greater than plus R, right? So minus I greater, तो overall तो electron withdraw ही हुआ ना. Yesterday we did na. Out of the two bad situations, we were selecting the one which is less bad. Same way, if I have a sigma complex orthopara versus meta, so meta I am having only minus I, whereas at orthopara I am having plus R and minus I. So relatively less electron is withdrawn when I place electrophile at orthopara, right? But if I compare the sigma complex's stability, the most stable is if there was no halogen. Then comes the orthoparas, then comes the meta. Okay, so that is why orthopara sigma complex is relatively less unstable than meta, but is not stable than benzene sigma complex. So fluoro, chloro, bromo, iodo are electron withdrawing groups. That is clear. And one more thing is there here. I'll discuss after 5 minutes. If CH3 is there, CH3 is plus H, that is hyperconjugation theta plus I, dena hi dena, always. So this one is orthopara directing and activating. CCl3 is meta and deactivating. It is reverse hyperconjugation and minus I. Overall, it will withdraw the electrons. Is that absolutely okay? Now, I wanted to discuss something here about these halogens. Let me add a page. What I wanted to discuss that we have decided that halogens are deactivating. That we have clear understanding. And OP directing. Okay. And OP directing. So it has both deactivating and orthopara directing. That part is clear. Now, if I want to compare the order of ES for fluorine, chlorine, bromine, and iodine. Okay. They are all less reactive for electrophilic attack as compared to benzene. That is done and dusted. But now amongst them, which is more deactivated or which is more activated, that is what we are saying. So see, fluorine is also doing plus R. Like all of them are doing plus R. And plus R is decreasing from F to I, right? Due to increase in size. And minus I is also decreasing. Please be very careful. Huh? This is important. Is also decreasing from fluorine to iodine. That is there. Now the point is, if both factors are decreasing, plus R is supporting the ES and minus I is opposing the ES. It is like decreasing the effect. Okay? But the decrease in plus R is dominating. Yeah, it means magnitude wise more, dominating over decrease in minus I from PHF to PHI. If I compare that, which is decreasing more? So please process. I'm going very slow so that you can process. The decrease in plus R is dominating. It means that pulling tendency is decreasing with a lesser magnitude and the donation tendency is decreasing with a higher magnitude. So overall, and thus overall donation is decreasing, है ना? Overall electron withdrawing nature or power of halogens is decreasing from PHF to PHI. Is that absolutely clear? That overall electron withdrawing nature or power I want to use for this of halogens is decreasing from PHF to PHI. Therefore, order of EAS rate is PHF is faster to react when PHCl, then PHBr, and then PHI. Take a screenshot that if we talk of halobenzenes, then relative जो deactivation है, it is increasing from fluorine to iodine. Fluorine is less deactivating than iodine. Absolutely clear? Usually all orthopara directing groups are activating and all meta directing groups are deactivating. That is a usual overlap of observation. There is no such rule, exception. Halogens are weakly deactivating, but orthopara, nitrosos, cinnamic, cinnamaldehyde, etc. are deactivating an orthopara. Okay. CO minus, SO3 minus, CO minus के अलावा SO3 minus also falls in this list. Okay, these are plus I and minus R. This group is orthopara directing and these groups are OP directing and activating. Clear? Now, if there are two groups already present on the ring and we have to introduce the third group, if both are activating, then more activating will control the third coming electrophile. If both are activating, see, CH3 is plus H, CMA3. Now let me see what these groups are. This one is plus H and plus I. So electron releasing. And this one is only plus I. There is no hyperconjugation. There is no hydrogen. So this group is more activating. Okay? If both are activating, the one which is more activating will control. So attack will be here. Clear? Now OH and NH2, if I compare, both are plus R greater than minus I group. Minus I group. Both have the same story. But you know that nitrogen being less electronegative will be better electron releaser. So the effective attacks will be at this position. Not ortho to OH. OCH3 and OCOR. Now here, these are entirely for the ring. There is no competition for this resonance. Whereas here I have a cross conjugation. It can donate here or it can donate here. So this is more activating. So I will have attack here. Is that absolutely clear? If both are activating, then more activating will control the third coming electrophile. But always pay attention. This we are talking for major products, certainly, not like all products. If you talk all, you have to consider all position of attack. In all of this, I was taking these at para position. But if you have two groups which are like meta, and now I want to put third electrophile, I will avoid this position and will have much better attack at these number of arrows means better attack, mild attack. Why? Steric will also be seen. Three continuous groups should always be avoided as far as possible. Absolutely clear. If one activating and one deactivating group is present, then the activating group will control the new electrophile. That is obvious. If one activating and one deactivating, then the new electrophile will be controlled by activating. So for here, this is activating, this is deactivating. So we'll have attack at these positions. OH and CHO, OH and CHO. Again, this will be less, this will be more because three continuous groups may or may not be preferred. Ortho to NH2. When there is one activating, one deactivating, ignore the deactivating completely. Don't think what is its suitable condition for this one, that this is coming ortho to nitro or meta to nitro. None of our concern. Just ignore the deactivating groups completely to have the final decision. Absolutely okay. Never ever consider any deactivating group's contribution usually completely for these type of setting when one activating and one deactivating is there. Okay. If both are deactivating like these, then the one which is lesser deactivating will control the effect. Now chlorine and NO2. So chlorine is less deactivating. Again, I'll say less here, more here. Okay, because three continuous groups were coming. Avoid attack of third electrophile at position such that the product will have all three groups adjacent. That is what we have already been practicing, that if two groups are there and you are introducing third, don't have a position like this. That is sterically crowded and will not have a major product consideration. Okay, before going to this, I want you to have a look at a very old comprehension of this concept, that where to attack thing is there. Just while teaching currently, I realize that this contribution, this particular comprehension will help you to get what I want to say. Just give me hardly few seconds and get me that PYQ for you. It was benzene only, and Friedel-Crafts was the question. And as you are in phase 2, doesn't matter that currently I have not taken Friedel-Crafts or what. Hai, you know what the thing should be. Just let me get that question. I think it was it this? I guess it was 2017, this question. I got the question. Just give me a second. Was it this one? Where steric was considered? Two questions I want to discuss. Let me bring it to the page and then I will discuss. Remember, this was 32. And the other question I want you to have a note is this one. I think it was this one. We'll check. I'll change the positions. Don't worry. Just let me bring the entire comprehension. And here comes the One more question. It was with this. So answers भी हमें चाहिए so that we can evaluate. Let me have the answers. What were the question numbers? 32 and 3940. 32 and 3940. So I'll take this. I guess इसमें इसके answers हैं. Okay. So what are my questions? Let me discuss. See, these two questions were based on steric and how they have framed. We'll check the answer later. First, let me take this one. And the language is also so very, like, you have to be very specific about what they are asking. I hope it is quite clear, a little blurry though. Trying to enlarge. I hope it is visible. Then I'll discuss the comprehension. See, the reactivity of compound Z. Z already is given with OH and CME3. Now, out of this is plus R greater than minus I. CME3 is only plus I. So, this is more activating. This is weak activating compared to this. This is strong. This part we have concluded. With different halogens under appropriate condition is given below. Now we have to take the reaction with different halogens. Okay, monohalo substituted derivative when X is I2. So they are getting only monohalo substitution when X is I2. Okay, so we predict that monohalo should be somewhere here rather than here or here because CME3 is bulky and here to not possible 3 continuous. Dihalo with bromine. So dihalo with bromine will go to this position. Orthopara, but not the center. And trihalo with chlorine. Okay, so OH, Cl, 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 and CME3. That is the possibility of trihalo. The observed pattern of electrophilic substitution can be explained by the steric effect of the halogens. Yes, you can see how chlorine and then how bromine and iodine, as the size is increasing, the choice of attack is coming into limitations. Like orthopara, this contains 3 with chlorine, not with bromine, and then iodine only 1. The steric effect of the tert butyl group is playing the role, certainly. Otherwise, if this was small, I can have an iodine here also. So there was a contribution of steric effect of tert butyl, certainly. The electronic effect of the phenolic group, that is the orthopara directive influence, that is, it is controlling the orientation of attack. So uska bhi importance hai. The electronic effect of tert butyl group, no. Because when activating group, once you decide, then there is no concern of this CME3 ka effect kya hoga. So this is not having any electronic effect. It is just influencing our answer for steric effect. Okay, one of a very good question from 2014, which is relevant to what we were just studying. Okay, now coming to this comprehension, let me take this also. And how they are solving it. Other question. I'll take the answer key also, don't worry. Just let me club it here. Yeah. I guess we have got it all right. The reaction of compound P, here is a compound P with CH3MgPr. I hope this is more clear now. In diethyl ether followed by addition of water gives Q. Okay, the compound Q on treatment with H2SO4 at 0 degree centigrade gives R. So when they are talking of excess of CH3MgPr attack, this will become a 3 degree alcohol. And then on treatment with concentrated H2SO4, you will have a Friedel-Crafts ring closure. So let me draw what could be the structure of Q. CME3. I will have ring closure here and two CH3s like this. Okay. The reaction of the compound Q on treatment with H2SO4 at 0 degree centigrade gives R. So this is my R. This is my R. The reaction of R with CH3COCl in the presence of anhydrous AlCl3 followed by water produces S. Now, when I treat this with CH3COCl, AlCl3, I have to do Friedel-Crafts. For this ring, how you will check the directive influence? See, CME3, only plus I. If I talk here, again it is a 0 alpha. So this is a group for the ring, but is only plus I, no hyperconjugation. This is directly attached. It is having 2 alpha H. So it is plus H and plus I. So who will be the winner? This is the winner, which will control the effect, which will control the attack. That will be ortho para. One ortho is blocked. Para is blocked. I am not left with any other position but this. You got the point? So here it will be attack. This acylation will bring CME3 and I will have here COCH3. So S should be this. Let us check 39. A. Okay. So that is what I was telling, how to decide. If, see, it was a case of 3 groups present on the ring and then you have to decide where to attack, not a very irrelevant question. 2017 it is. The reaction, this was also a very confusing part. The reactions Q2R was Friedel-Crafts and R2SR and R2SR. So Q2R was a Friedel-Crafts alkylation because alcohol at के आया, so Friedel-Crafts alkylation, and then is a Friedel-Crafts acylation. So we have alkylation followed by acylation. For this, answer is D. Is that clear? This answer is D. So for 39 answer is A, 40 answer is D. So now I hope you have got my point that how to use the effect. And it is asked in JEE, so you cannot ignore it. These two questions are of direct relevance. Just wait, Shubhangi. Yes, Shubhangi, I have unmuted you. Please ask.
Ma'am, in the 40th question, we will have dehydration along with...
also. I was waiting. Yes. Shubhangi, when we talk of a net reaction, like they are considering the Friedel-Crafts total reaction. So there we will not consider the word dehydration usually. Like what I want to say is, there is H here. And I think the thing was like this, no? And this was CME3. Yes. So when here they consider, it is not, this is not taken as dehydration. Dehydration is considered when there is alkene formation, eliminations. This is not, this is substitution. So they do not take it as a dehydration. Kahan gaya wo point? Dehydration. The most appropriate by your logic could have been C.
Yes, ma'am.
When they are giving name reactions, then do not take these as a part. Dehydration as a name reaction is an alkene formation reaction.
Okay, ma'am.
Okay.
Yes.
So anything else, Shubhangi? Can I mute you? Okay, already done. Okay. So where were we? So I was teaching you that if two groups are present, how to handle. So make it a point. Mark the groups. Take their effect into consideration and then you decide. And please, when there are options, read them very carefully. Read them very carefully. That is the key. Okay. Coming to some other question. Yes, Maimuna, what do you want to ask? Is there anything you want to ask? You raise your hand. Okay, so I assume there is no one. Let us come back to where we were. So I was telling ki similar halogenation of which of the following will yield meta-substituted product with respect to methyl group as a major. Okay, with respect to CH3, I want a meta-substituted product. CH3 को meta होना चाहिए. So if you see CH3 and CHO, now you will have relatively this as a weak, this is a activating and this as a deactivating. So I will attack here, I will attack here. So it is not meta to CH3. Similarly, the case is here, I will attack here and here. So it is not meta to CH3. Here and here again, not meta to CH3. Coming here, CH3 is not the deciding factor. OH is the one. So I'll attack here and here. And so meta to CH3 is now into case. And so answer is C. Is that absolutely okay? One more thing I wanted to tell, that sometimes these questions come like for dye substitution, that let me formulate the language. For example, if I want to give that there are 3 isomers of xylene. And 3 isomers of xylene. And on introduction of third electrophile, which will give only one product. That type of question. Let me solve. When we give this type of language, there you don't consider major minor. So I have ortho. You have to consider all possible cases. Either they should give one product as major or something, then only you will limit yourself. For this, you will simply consider that how many cases are possible. So you'll say CH3, a new electrophile could come here. Whether it is 1%, 2%, that is not our concern, but can come here or come here. If I go to other 2 positions, it will be repeat of these 2. So here you will say 2 products are formed. Similarly, for this one, you will report, yes, I know that very, very less center mein maine lagaya. Yes. But when this type of question, how many products, then you have to consider this. And one more, in which meta. So this you will report there are 3 products formed. For this, whichever position you will attack, you will have only one IUPAC name, and this is decided by by IUPAC name. So answer is paraxylene. Okay, so if this type of language comes that on third electrophilic attack you have 2 isomers obtained, 3 isomers obtained, then it is not about major or minor. It is simply about the different positional isomers obtained, and corresponding to that they are asking. ठीक? Yes, I could not pronounce the name. It is Thwha. Thwha. Yes, what do you want to ask? Yeah. Is it anything that you want to ask? Okay, I assume after Shubhangi, I'm having a problem. They just raise their hand and they don't ask anything. So again, we'll go back to I'll not allow anyone in between, and we will ask at the end of the class only. Only those who will be sincere to ask will be allowed then. Okay, let me move further. So we were at the point where I was telling this is another language of question. This we have discussed. Now come to specific reactions for nitration. nothing much. Mainly the question confusion things we are already done. These are general properties. So you have concentrated H2SO4 or HNO3 dono combination. It is called nitrating mixture. 50 to 60 degrees centigrade, introduction of first nitro group takes place. Now nitro is deactivating. So if I want to introduce next, the temperature will be higher, the time required will be higher, and I can introduce the dinitro. Theoretically, I can introduce third nitro also, but it takes around 100 degrees centigrade, and for 5 days, I have to treat with nitrating mixture for 100 degrees centigrade. Then I can have introduction of third nitro. But as you know, this is almost next to impossible. So this is not the right method to introduce a third nitro. If you want to introduce third nitro, this is not what you will do. We'll have another method that we'll discuss. So mechanism, sulfonic acid, H2SO4, sulfuric acid and HNO3, stronger acid, H2SO4, protonates, weaker acid, and we have formation of this loss of water, nitronium ion. So the electrophile is nitronium. Everything is now monotonous. Nitronium ion attack, we have a sigma complex, and the product is called oil of merbane. It is a very light yellow color compound. Okay, it is light yellow compound. Take important points to remember, nitrating mixture also act as a strong oxidizing agent. So with phenol and aniline, we have to maintain very low temperature, otherwise oxidation products will dominate. Okay, like with nitrating mixture and aniline reaction. Please remember this, very, very important. Okay, this is very, very important. With aniline, when we treat concentrated H2SO4 and HNO3, we have meta product at 47 and para product at 51. But ortho is only 2 degree. So if we are asked about the yield, I'll say para, meta, and then comes the ortho. Now, why this is so? So basically under acidic conditions, aniline will also have this equilibrium aniline and anilinium ion. Now, this could be attacked or this could be attacked. But if this has become comparative or very high in concentration, NH3 plus is a deactivating and meta directing. So meta products will be formed. Okay, if attacks are on NH2, then the answers are ortho and para. With anilinium, answers are meta. This observation of products still says that this is more than this. If you change NH2 to NHME2 or a more basic aniline, I make it NHME or NME2, then meta will become major. Okay, we can use masking of aniline and phenol to avoid oxidations totally. So yes, if masking means we'll introduce acetylation, we'll decrease the activity of the ring so oxidation can be avoided. And then with the help of nitrating mixture, you can have orthopara attack. Wait, Ashish, let me complete. Then we'll talk. So this nitrating mixture, now this is relatively less activating than NH2. Better, no need to worry because at least now anilinium is not formed, deactivation is not happening. I'm having para NO2. Okay, and then we'll hydrolyze it and obtain NH2. So you can have acetyl group, acyl group, or you can even mask by tosyl group, THCl. That is also a choice, and in fact a better choice, right? Tosyl group is even a better choice because tosyl group will make our ring further deactivated, or rather I should say less activated, like this. So this has to go here and here. So ring is less activated, and oxidation can be avoided. Otherwise, we lose large part of aniline. Slight temperature be increase hua, then a charcoal like black tarry substance is obtained with aniline and phenol. To be honest, with phenol, we don't use this method of nitration. We don't use. Okay. Again, by masking, you can do very good. That is excellent method. Now coming to this page. This first, this, then we'll go there. Phenol may, as I said, I will not use nitrating mixture. Otherwise, I lose phenol entirely to oxidation. So I'll use just concentrated HNO3 and I'll get picric acid directly. No need to add H2SO4. Please mark this very carefully or take a screenshot. If you have a dilute HNO3, you are having ortho-para-nitrophenol, out of which major is ortho due to intramolecular H bonding, can be separated by steam distillation. Ortho is the one which will go with steam. With concentrated HNO3, we have picric acid, 2,4,6-trinitrophenol. pK less than 1. Okay. Other method is you can have dilute HNO2. Now, dilute HNO2, if I'll take, this will be source of NO plus, nitrosonium ion. So I'll have ortho-para-nitrosonium, which easily get oxidized to orthonitro and paranitrophenol. These are our methods to have nitrophenols instead of having nitrating mixture directly. That is not the right method. One more addition, nitrobenzene can be reduced to aniline by iron in HCl, tin HCl, zinc amalgam HCl, nickel hydrogen, and all these methods. Any of these will reduce it to aniline. Okay. Last here, toluene we treat with nitrating mixture. Then we get TNT, trinitrotoluene. Now, as I said, for making trinitrobenzene thing, we will have another method. So what we do is, we treat it now with KMNO4. So it will become COOH, NO2, NO2 and NO2. And you just heat it. See how stable this carbon ion is due to 3-nitro. It will decarboxylate by itself. Or if you want, you can add soda lime. So this is how we prepare trinitrobenzene these days. We do not go by nitrobenzene, then further nitration and further nitration. That doesn't work for our yield. Absolutely okay. Coming to some other question which appeared, arrange the following in increasing order of reactivity towards nitration. Similar questions appeared for our this advance also, but long time back. These days, these questions are getting down and down, but mains, yes, regular. So, in increasing order of reactivity towards nitration, first draw the structures. Paraxylene. So, paraxylene is CH3, CH3. Mesitylene. You have to remember the word. Benzene, just basic. Bromobenzene. And last is nitrobenzene. So first thing you have to do is draw the structures. Second thing, you have to see the effect of the groups. So there are CH3. So plus H greater than plus I groups. Plus H greater than plus I groups. This is reference, that is scale 0. Bromine. Yes, overall it is a resonance group, but minus I dominates over plus R. Nitro minus R dominates over minus I. Once you decide this, you have two activating and deactivating groups. 3 alkyl will be best, so C should be the best of all. Then comes the A. I hope you agree with this. Then comes the reference. Okay, halobenzene is poor. It is not stronger or activated. It is weaker. And then comes the D. CAEBD. CAEBD. Answer is B. Okay, this type of questions you can expect. This is again a very common type. What will be the major product in the following? So see, you have two benzene rings, and for such questions, the trick they use is, what trick they use is a very common trick of paper, etc. I'll tell you. They do this NHPH. Okay, and then they will ask what will be the product or whether it is activating or deactivating. Now see, you have two rings. You have a ring number 1 which is activated. Why? Because NH is attached and OP, and this is a ring which is deactivated and meta directed. So out of these, of course, this will be attacked, not the deactivated ring. This presentation will confuse you. You will be focused mostly on the ring which is drawn, not which is there but is written intentionally so that you just miss it out. So whenever such questions are there, please pay full attention to the structure. Okay, so this ring will be attacked and orthopara. So para is best. So C seems to be okay. Ortho, I don't even see the product. So C is correct. Clear? But this is a trick. Please don't fall for it. Next comes to sulfonation of benzene. We use concentrated H2SO4 heat, right? 60 degrees centigrade. Introduction of sulfonic acid SO3H 160. Again going back ipso. Mechanism is, you can see, nothing important as such, or in phase 2 it is nothing important. Phase 1 I would have taken in detail. I can have either of the two electrophiles, either HSO3H or SO3. Either could be there. You can use better yield ke liye, you can use oleum, right? Oleum would have been even better. That is H2S2O7 extra SO3 dissolve. That would give me better yield. Benzene sulfonic acid is formed. Backward reaction is also an ES where H plus is replacing SO3H. When in an ES, H plus replaces existing group, then it is called ipso. Other than SO3H, you can have COH and is an important group displaced in ipso reaction. Okay? Halogenation of benzene. Coming to this. As it is easily introducible and removable, so SO3H is used for masking para positions because it is easily introduced and removed. What I want to say, for example, I want to convert this to just one bromine. Now you know that this conversion is relatively problematic because para will be preferred. If I go for direct bromine in CS2, I will have orthopara in which para will be major. So it is not so good. What I'll do is I will introduce concentrated H2SO4 and will have SO3H introduced. Right? We'll have this introduced. Now I will add bromine in CS2. So now para is already blocked. So I can have bromine here. And now I will heat it with dilute H2SO4 at 160 degrees centigrade. So ipso will take place and OH bromine. So this is what I meant, that masking of para position is done by this method. I want to take a few seconds break from this because all of a sudden I realized in NCERT in chapter phenol, there is something important that we should know. Phenol is chapter 2nd. Just let me reach there what I wanted, because may not be immediately this PTA, but It's time. You should know all. Give me a second. I'll share the screen. Is it? Yes, it has come, I guess. So what I wanted to tell here that, see, this is a very important topic in 12th NCRT phenol. Direct concentrated HNO3, picric acid, 2,4,6 trinitrophenol. Bromine in CS2, major, minor. Major is para, that we have already discussed. What I want to discuss, just let me move. Bromine, 2,4,6 tribromophenol. That is fine. I remember somewhere in sulfonation, they have mentioned that I'm missing out something or what. I have a memory that they have given only 2SO3H introduced somewhere. Okay, here it is. I'm not missing out. It is here. Nowadays, picric acid is prepared by treating phenol first with concentrated sulfuric acid, which converts to phenol 2,4-disulfonic acid. Okay, so when picric acid question is asked, please make it clear. First form phenol 2,4-disulfonic and then with concentrated HNO3. Ipsol here takes place as SO3H is displaced by NO2 plus. And you have 2,4,6 trinitrophenol formed. This is what I want to tell, that if picric acid question is there, then don't stop the reaction at monosulfonation. There they consider 2 and 4 disulfonation is there in that picric acid thing. Okay, that was important to be taken care of. Coming to next point, halogenation. Now let's move to halogenation. So if where are we? I want to check how much is left. Will I be able to complete today or not? This we have done. We have done halogenation. So we are somewhere at 29 page number. Let me check. 29, I guess. Right. And total pages are 48. So let's try. We still have some time left. I want ki all things ho jaye. Ek baar revise hai na. So halogenation of benzene. When we talk of halogenation, we take these type of catalyst, iron, FeCl3 or AlCl3, and these halogens. Of course, chlorine, bromine only are suitable. We don't take iodine or we don't take fluorine. Fluorine has its own issues. Iodine has its own. We'll discuss. And we get halobenzene. Halogen, AlCl3 attacked like this. A complete bond will be broken if a Lewis acid used is strong. So X plus, and we get attack and this. Now, if it was fluorine, then this type of thing is not happening, this whole thing. So fluorine is not possible. With iodine, reaction is highly reversible and gives very poor yield. So fluorobenzene, if you want to prepare, then you have only one method. And fluorobenzene cannot be prepared by this method. Only method to prepare fluorobenzene is by Ball-Schiemann reaction, in which pH N2 plus Cl minus is heated with HBF4. We get a precipitate, diazonium tetrafluoroborate, and we heat and form fluorobenzene and nitrogen is released. For iodination also, we depend on diazonium, direct reaction with Ki, but no name like Ball-Schiemann. Okay, again a very important note. If I take iron and bromine, I'll get bromobenzene. But bromine in CCl4, bromine in water, no reaction, because you remember na, these are tests of unsaturation. With them, no reaction. With this, yes. Okay. Bromine in water on phenol is yes. There is a reaction, 2,4,6 tribromophenol. Aniline, there is a reaction, 2,4,6 tribromo. Aniline, both are white precipitates. Okay. With phenol, bromine in CS2, orthobromo and parabromo. But with aniline, even in CS2, you get 2,4,6 tribromo, aniline as a product. Okay, take screenshot of this page. If I have a side chain with unsaturation, then bromine in CCl4, yes, you will have side addition. Bromine water, yes. Bromine and iron also do not go on the ring now, because Br plus will preferably attack the side chain. bromine HNO for this benzylic attack. NBS, okay. Chlorine HNO, SO2Cl2, tertiary butynyl chloride or NCS, all these type of attack. Clear? Again, a very important point we are had. Chlorine excess is taken. Then you have all chlorine, but this is done by EAS. See, it is having no Cl, no H. The formula for this is C6Cl6. There is no hydrogen. Okay, it is hexachlorobenzene. If I have an excess chlorine and I take HNO, then it is addition. You will have hydrogen at all these places like this. Formula is C6H6Cl6 benzene hexachloride. This is a common name. This was IUPAC. Okay, and this took by radical addition reaction. This is radical addition reaction. This was electrophilic aromatic substitution. Now, this BHC has 8 geometrical isomers, out of which only one is optically active, total 9. Gamexine, lindane, insecticide, pesticide, respectively, are from these stereoisomers only, this BHC. Okay. Coming to one more question. In the presence of sunlight, benzene reacts with chlorine to give product X. The number of hydrogens in X is. See, when they are referring to in place of sunlight, it means it is a radical reaction. Chlorine, sunlight. So they are asking formation of this. Okay. The number of hydrogens in X is. Answer is 6 because this is C6H6Cl6. Clear? One more question. Identify correct ABC in the given reaction sequence. First is nitration. So I expect here nitrobenzene is formed. Chlorine, meta orientation. So NO2 will go to meta. And then iron HCl. It will reduce NO2 to NH2. So this seems to be correct. Nitro, metachloronitro, and metachloroamino. So answer should be A. Right? Coming to the most important reaction, I'll say is Friedel-Crafts reaction of this week. Friedel-Crafts alkylation and Friedel-Crafts acylation. Alkylation in presence of Lewis acid. We form an adduct which form a carbocation. If there is a possibility of rearrangement, it will rearrange and then direct ES, attack and loss. Okay. If the Lewis acid is weak, then if Lewis acid is weak like FeCl3, FeBr3, then rearrangement of carbocations are absent as adduct will attack directly. Carbon plus is not formed. But if it is strong, then a full carbocation is formed and rearrangement is possible. Okay. Other sources, alkenes H plus, you can have a carbocation, alcohol H2SO4, alcohol BF3. But mind it, alcohol BF3 form a full carbocation. Let me add. But if I have RX plus BF3, then it is not full carbocation. You will have adduct only. With alkyl halides, it forms adduct. With alcohol, it forms because of high bond dissociation energy of boron oxygen. There it forms a complete carbocation. The cyclopropane can also attack by the adduct formation, not a full carbocation. Take other points. As alkyl is an activating group, so polyalkylation will take place. Yes. For same alkyl with AlCl3, order of reactivity is RF. Where is it? RF, RCl, RBr, RI due to Lewis base nature. Friedel-Crafts fails for PHNH2 as it has a base formed and it forms adducts with the Lewis acid used. But it does not fail for phenol. With phenol, you take excess of AlCl3 and do the reaction. Okay. Friedel-Crafts fails for strongly deactivated rings like PHSO3H, PHNO2, PHCOR and all these. Okay, it fails. With phenol, we have to take excess of Lewis acid and reaction will take place. Again, a very important question. The major product of the following. See, H2SO4 they will add. Now the point is where to add. Okay. So H plus when you add, I have 2 degree and I have 1 degree. Several students this year got confused that nitro is there. So should we make this type of carbocation as major? No, only when nitro is directly attached to bond, then only you go for anti-Markovnikov additions. ठीक? Otherwise, if one distance is there, go back to Markovnikov. So this will be formed, and answer is this, right? So what I'm saying is like this. If you have COOH, CH double bond, CH2, okay, Sino, CH double bond, CH2, direct attached to double bond, etc. Then anti-Markovnikov. Otherwise, Markovnikov. Okay. For example, even for these, if we are asked to add HBr for such, then you have anti-Markovnikov CN, CH2, CH2Br. And the reason is the resonance. CH double bond, CH2. Right? You can see how it is behaving. It is Br minus will attack here like this. But if it is one bond is there, then do not take anti-Markovnikov, take Markovnikov. This type of attack. Absolutely clear. Coming to other question. In Friedel-Crafts alkylation of aniline, one gets of aniline. Alkylated product with orthopara, no. Secondary amine, no. An amide, positively charged nitrogen at benzene ring. That is what we just said, that if I have aniline and we take AlCl3, so instead of alkyl halide, Rx, it start attacking at this AlCl3 plus and minus. As a result, this ring gets deactivated and no further attacks take place. Okay. And yes, there are certain groups which will not participate in Friedel-Crafts. You cannot generate electrophile with PHX, CH2 double bond, CHX. Do not participate to give E plus in Friedel-Crafts reaction. They do not participate. Take. Next, moving to acylation. Similar notes, you get acyl group. Acyl group is very, very stable. This octet complete group is more stable than even 3 degree alkyl carbocation or any such. Okay, it is extremely stable carbocation. It attacks like any other normal electrophile and you get a deactivated ring. See, carbonyl. So further attack of electrophile will not be there, which was a problem in alkylation. As PHCOR cannot undergo Friedel-Crafts reaction, so mono-substituted products will be obtained. And no rearrangement, as this is the very extremely stable carbocation. Other sources of acylation are, you can take anhydrides. Acylium group is formed and can take attack. Esters can give both alkylation and acylation. Usually alkylation is major. See, this is an ester. Now, if I have LCl3, this oxygen is having more del minus due to resonance. So my preferred attack is here. As a result, this is the site where benzene will attack. Okay, so alkylation dominates. This was asked in 2019 mains. But if this position, this carbonyl is sterically crowded, see, 3,3 phenyl. So this is ortho, both sides covered, substituted, stopped. So now it cannot, LCl3 cannot attack here. I cannot have that type of thing. So now I have a problem. I have to attack with this oxygen and a new acylium, right? Intramolecular attack This is advanced 2020 question. Is that absolutely clear? So how alkylation and acylation? So first you prefer attack on double bonded oxygen. If it is covered or sterically crowded, then you take attack at this single bonded oxygen. Okay. Now this was the question which was asked in 2019. So this I have already discussed in detail, that OH and CH3. So OH, this position will be attacked. This again 3 continuous group should not be taken. So anything in which OH ka para is attacked should be the answer, which all of them seems to be appropriate. OH ki para, OH ka para, OH ka para, OH ka para. This is a little crowded. See, 1, 2, 3, 4, all 4 groups in a row. So this cannot be the answer. Rest 3 are still in the race. Okay. Now, as I have just told you, first it should be alkylation. First it should be alkylation. OH ka para position should have alkyl. OH ki para should have alkyl, alkyl, alkyl. So this acyl. So this is gone. Now I am left with A and B. Now I have to draw that OH ki para position. So if I take this CH3 here, here is attack. So 1, 2, 3. 1, 2, 3. And then I have CO. Then I have COOH. Okay. Now again AlCl3 is there. So AlCl3 will again form a duct here. Plus will be created. Now I can attack here or here. Ring closure is irrespective of direction, will attack at ortho. So I'll attack here. So OH, CH3. It will become OH because this H will release. Na? So 2 OH when there are 2 OH, one will be definitely released. Am I getting correct structure? Right, 1, 2, 3, and this is the 4th one, and this, yes. So answer is coming A. Here the ring is wrong. Okay, though the directions of attack are considered correct. This was 2019 mains, and they have taken this A as an answer. Okay, moving further, for same alkyl group, AlCl3, order RF, RCl, RBr. This is a copy paste of what we were writing there. Same things will continue. One extra point I will add is Me3CCOCl, AlCl3. Yes, the more stable carbocation is this. Okay, but as this is also stable and there was a slight push, this reaction happens due to delta S of the reaction being positive. This molecule is breaking, carbon monoxide is stable, gaseous, released. But it takes some time. So if I bring benzene, I'll have this. If the ring was activated, say OMe, then this reaction will not happen. This directly will attack. Okay, so this happens only with normal benzene, where there is a time and you have a loss of CO due to increase in entropy. Otherwise, this reaction is not common. Okay, there is a possibility of intramolecular Fiddlecraft. As you can see, ring closure. Okay, similarly here. Yes, one more thing I want to tell you. This is a very common question. They give benzene and they give something like COCl and CH2Cl. It originally came from this was originally a question from INCHO, but now it is appearing everywhere. It was a big question, uska one part tha. And AlCl3. So I can form both carbocation, na, acylium or CH2 plus. So what is observed is acylation takes place. You will find that this will be gone. Acylation will take place. not alkylation. Is that clear? This is formed. Oxidation of benzene. Anything attached to ring will always be oxidized with acidic or alkaline KMnO4, or even I should say acidic K2Cr2O7, any of these. Everything ends to benzoic acid. Till I have one hydrogen here when the things are sp3. When they become sp2, then I'm not even bothered about that H over there. Okay. So, but if it is Cr3, then this is not formed. Okay. Otherwise, always this is formed. If I talk of naphthalene, then either of the ring will undergo the breakage and I'll have phthalic acid. The other component goes to oxalic acid, but oxalic acid in KMnO4 is usually oxidized to CO2. So it depends what reagent is there. Now, but if the naphthalene is substituted, which ring will break? How to decide? The ring which has more electron density will undergo the breakage. Because oxidation is loss of electron. So only that one which has more electron will undergo breakage. So nitro will remain intact here and this is gone. Here phenol will be gone. Benzene, because this is more activated. So see the difference in product. Here nitro group is there in acid, here not. Okay. Correct sequence of reagents used in preparation of 4-bromo-2-nitroethyl benzene. From benzene, 4-bromo-2-nitroethyl benzene. Let me draw the structure. 4-bromo-2-nitroethyl benzene. This we have to prepare from benzene. First thing, first nitration karai and then Friedel-Crafts. Always a fail because first nitration, nitrobenzene is a solvent of Friedel-Crafts. It can never be the reactant for Friedel-Crafts. Okay, it is always the solvent. So never ever we can have nitrobenzene as a first step and then Friedel-Crafts. Correct? So then comes the bromination followed by Friedel-Crafts acylation. That is a possibility. But then nitration at zinc HCl. That is wrong. Zinc HCl will reduce NO2 to NH2 also. Acylation. Yes, yo, wait. In the end, I'll ask you. Till then, you note down your doubt and in the end, you can ask. So first is a Friedel-Crafts acylation, then bromination. Not good because meta directing ho jayega. If I have a Friedel-Crafts acylation, so COCH3. And if then you introduce bromine, it will go to meta. Like this, which is not the answer. Last. So first they have done acylation. Then zinc amalgam HCl. Zinc amalgam is Wolff-Kishner. So that is right. That is how they will have ethyl benzene. Now introducing bromine. Yes, para will be the product. Then nitro, more activated. So nitro will come here. So answer is D. Okay, but remember for nitrobenzene, Friedel-Crafts will fail. It is the solvent of Friedel-Crafts. Absolutely clear? So this brings us to the end. Yesterday's point I want to add. We have discussed that reaction, any electrophilic reaction on alkenes is faster than alkynes. So if I have one equivalent of HBr, I will add that one equivalent of HBr to double bond like this. Okay, because more stable carbocation instead of double bond, triple bond. Triple bond will form vinylic. So I will add it to like this. But if the triple bond and double bond are in conjugation, then please remember that then Alkyne is the one which is adding the electrophile. This is only when the double and triple bond in conjugation. Otherwise, it is the double bond which will add the electrophile first. Correct? I hope this is all good. Okay, so now you can ask the doubts. I'm allowing you. Please raise your hands. Yo-Yo was the one who was asking. Ashish was asking. There were two people. So Ashish, yes, I am unmuting you. First, start with Ashish. Yes, Ashish,
In
loud.
nitration of aniline, you have mentioned that in ortho position there is only 2%.
Yes,
Yeah,
yes, that is there. Bilkul, absolutely. Yes.
yeah.
So it is given in NCRT and it is correct. What is the problem? First, tell me that. It is yes,
You
2% only.
Yeah, you have mentioned that there is a reason for it. There is a formation of NH3 plus. Why it can't reduce para position also? Na?
Why can't there be decrease in para position
Yeah,
also?
that is my.
Actually, this is an electron withdrawing. To my understanding, what I got is that this NH3 plus is responsible for NO2, and when it is NH2, probably due to some, if I bring closer NO2 plus or overall the acidic conditions, then I assume, I didn't read it anywhere, huh? I assume that when it comes to closer, usually this NO2 plus then attacks the NH2 itself,
Yeah, okay.
because nitrogen is also a good donor and it
Yeah.
attacks at this position only, and then it again becomes deactivated. So
Okay.
either when it comes to ortho attack, it attacks on nitrogen, and then for further strong heating, it may decompose or it may dissociate and go back to para position. That is why.
Okay. Okay. Ma'am.
But this, I didn't read in any book regarding this that this could be the reason. I read that any electrophile, if ever attacks on aniline, it preferably first attack on NH2 itself. This I read. So in combination of these two facts, I am giving you this reasoning.
Okay.
Okay, Ashish?
Okay, ma'am.
Okay, bete. Okay, so next I will ask Yo-Yo to unmute. Yes, Yo-Yo. Yes, Yo-Yo, you rose your hand. You were asking something. Please unmute yourself. I have allowed you. And ask your doubt. Okay, I think there is some issue at Yo-Yo and she or he could not unmute. So let me ask Preetham. Preetham,
Sorry, ma'am, I had the same doubt as Ashish regarding this. Clarified.
okay. So is
Thank
it
you.
okay?
Yes,
Okay. Okay. And I also had one more hand. I think these were the anyone else? Anyone else want to ask? Please raise your hand. I had only 3, 4 hands. Anyone else? Shiva, is there anything? Yesterday you asked very good doubts.
Ma'am, like today I don't have doubts.
Today you don't have any. Anyone else? All good? Okay, so those who do not have any doubt can leave, and those who have doubt and are wanting to ask can stay back. If you want to listen the doubts, you can stay, of course. That is your choice. Like lecture wise, I'm done. If anyone wants to ask any doubt, they can stay back. Others can start leaving. Okay, one hand I got. Let me. Yes, Shiva.
Ma'am, can you explain what is like regio-selective, stereo-selective, and stereo-specific difference?
Yes, I can. Wait, let me ask for those people who is there anyone with the benzene doubt, or else I'll go to that. I see no other hand. Shiva, I could hear that you asked that what is regioselective and what is stereoselective, that thing you asked, hai na? Not the
Yes,
regio,
ma'am.
na? Was it regio also in the list?
Yes, ma'am. Regio is also on the list.
Okay. So, okay, let me do it. So, as the name itself suggests, selective. Okay. See, regio selective. I split it into two, though technically it is written as a one word. Selective, it means selection. Regio matlab region mein selection. Selection in the region. So, when in a reaction, different positional isomers are formed, regional isomers. Okay, positional isomers are possible, are formed. Rather, I should say, are possible as a product, but any one positional isomer is obtained either as exclusive, yani sole, or major product. Then reaction is called regioselective. That the reaction is selective with respect to the regional isomers. Then it is called regioselective. And its example are Markovnikov and anti-Markovnikov additions. Okay, anti-Markovnikov, or you can have that Sedzev and Hoffman thing. These are regioselective. Okay. Coming to what is stereospecific and stereoselective. Now be very careful. Stereospecific is a term used when specific stereoisomer of reactant give specific stereoisomer of product. Then reaction is called stereospecific. Okay, here the compulsion that the reactant should also have a stereoisomers compulsorily to be used. For example, when we talk of, say, this cis plus bromine addition in CCl4. And so you get a racemic mixture of bromine. I'm not drawing the geo, this wedge dash, just racemic mixture of this product. If you have a trans, you will have a meso. And if you have a trans of the same thing, you will have meso product of this. So I'm starting with a specific stereoisomer of reactant and ending to specific stereo combination of product. Then it is stereospecific. Coming to stereo selective. Now here I will not talk about the reactant ka stereoisomerism. No. If product can have different stereoisomers and any one type is obtained as exclusive or sole in the reaction, then reaction is called stereoselective. Now see the difference. In specific, I was talking about reactant stereospecificity also. For example, if I have PHCH, OH, CH3. Now see, this is chiral. Whether I start with dextro or I start with levo, if I have a concentrated H2SO4 heating, I will have this as a major product. So this reaction shows that there are different possible, this as a minor. So whether I start with whatever, I am having a specific stereoisomer obtained. So this reaction is stereoselective, but not stereospecific. Right? So I can conclude all stereospecific are always stereoselective, but reverse not always true. Right? There may be reactions like this is also stereoselective because a specific isomer is formed. So it is, this reaction is both stereospecific and stereoselective. But this is only specific. Is that clear, Shiva? You can unmute.
Yes, ma'am. It's clear, ma'am.
Okay, this is a very important confusion. I'll split it into 2 pages. You can take a screenshot if required.
Yes, ma'am.
Taken?
I took it. Yes, ma'am.
Okay. And here also?